Share screen. All right. And that's the right thing. That 410 number is my standard number now. So
make sure you have the right audio input because it said you're using computer audio.
Did it say that? Okay. That's somewhere here, right? Audio options. Computer audio connected. No, it's not. It's lying. Good. USB audio and see it picking it up. Good. Thank you. Yeah, that seems to automatically do that now. It's pretty nice. All right. And the one thing I do not know is how to tell who's in. Oh, there's people in. My goodness. Somebody named Cam is already in. Cool. Okay. Well, good. There's even a chat window someplace. I'm hopefully going to get to the point. Ah, here's chat. Good. All right. So, I might notice questions here. It's possible. So we'll see what comes of this all. All right. So, all right. Let me just talk about the news for a few minutes. We got about 5 minutes before the official class time. There's always a lot of exciting news. This one was interesting. That one's possibly interesting. This one's kind of fun. And this one's pretty cool. That one too. Lots and lots of good things.
Did you see that AI, using AI to do correlation attacks on blockchains?
Nope, didn't see anything about it. If you send me a link, maybe I should check it out. So, okay, it might be somewhere in my mail. So here, this is a book on artificial intelligence for security professionals, a free ebook. So it's in today's news. I haven't read it, but the price is right. And it's from Cylance, and that's a legit company, so I would assume this is pretty good stuff. I know almost nothing about AI, but they're absolutely right. We all better start learning. AI is coming. The next generation of IDSs is going to be AI. It's all over the place. So it's time to get on board. We should probably have a class in AI if we don't. I don't know any teacher ready for it, but we got a bunch of stuff we got to do. Cloud computing and AI. These things are on the horizon. And either art department. Anyway, so this is the start. If you want to get ahead, probably within the next couple of years, we'll come up with some kind of class because it's important and we should do it. So here's an interesting article. It's something called The Week. What's funny is they don't understand anything about Bitcoin. Everything they say here is wrong. It's kind of hilarious. No government, no monitoring, no transaction fees. Well, that's news to me. I had to pay $4 every time I made a Bitcoin transaction. And that transaction fee is just going up. It's kind of funny down here. There's more garbage down here. You solve complicated algorithms, which is not all that true. What's funny is, yeah, highly encrypted transaction data. Bitcoin transaction data is not encrypted at all. Everything is public. It is signed. But, you know, this is very common. There was even a Security Plus textbook I used to use where the author of the book didn't know the difference between cryptography and hashing, encryption and hashing, or at least mixed the two randomly. In the early chapters, he got very angry at me when I put a bad Amazon review saying, don't bother with a book like this. Anyway, so the person who wrote the summary does not understand Bitcoin, but they have pictures of the Bitcoin mines in China, which are interesting. So here they are in some place rural in China where they can get a lot of power from this river. And there's the mine. Just rack after rack of servers, of course. Apparently they spill the water on the floor and everything. And here they are, many, many servers, just like any other server farm. Discarded mining machine boxes pile up. Because, of course, they're making money and they sleep on site, you know, usual stuff. Pretty much like any other data center, actually. So this is one thing I've seen in the last 2 months. Teen Vogue is becoming a really good security magazine. I have no idea how this happened, but Teen Vogue has had a lot of great ITs. And here it is. This woman is a security researcher, and she's not a joke. Amanda Brousseau, she's done real stuff. She talks about why girls should get in security and so on. One of the advantages, you can code from anywhere and so on. But anyway, I was surprised when they started posting teen vote articles about security, and they're good. And various people say sarcastically, what made you think it wouldn't be good? And I said, well, somehow I had the impression that Teen Vogue was not a technical resource, but it is apparently. They've had a lot of good stuff. Anyway, so this guy was ignoring somebody and took a look. I've heard of this guy. Simon Smith is one of the latest security charlatans. So like many security charlatans, his main shtick is to blame all the others. So you should, somebody joined the live stream. Good, it's working. Anyway, so, all right. So hackers, researchers, pen testers are not cybersecurity. In case you're interested, everything you're learning from me is garbage. You should quit and go work for this guy. Anyway, so that's good time, good clean fun. And this one was interesting. Somebody tried to sue Apple. Yeah, you got to find your volume control. Somebody tried to sue Apple because they're texting and crashed a car. And it would be important if they had won, but they did not win. The judge made what seems like a common sense decision saying the chain of causation is far too attenuated. It's not Apple's fault that you're texting while you're driving to wreck your car, which makes me happy anyway. It seems to me like it's not McDonald's fault if you pour coffee down your shorts either. This is, there's a thing called due care where you're supposed to take reasonable caution in using whatever technology you have. This is pretty interesting. This is one of the British tabloid magazines half full of soft pornography, but in between they have something more or less resembling news. And these guys have been analyzing. I didn't know if this, but they say Google Android is constantly got the microphone turned on and it's listening for the trigger phrase, which is like, okay, Google. And if it finds anything that it interprets as okay, Google, it turns on the microphone and records 10 or 20 seconds of audio, and then it sends it up to the server. Now, this is how they all work because AI cannot run on your phone. AI runs in the cloud. All it can do is harvest the data and send it up to the cloud. And this is, of course, the wave of the future, which is why Windows 10 is accused of huge privacy violations because a lot of Windows 10 services are in the cloud. So when you do things, it sends it up to the cloud and does things like check to see if a URL is bad or not. So it's constantly sending everything you do up to Microsoft, which when people detected, they said Microsoft is intruding on our privacy, which is possible. But the other side of it is what Microsoft said. They say we're offering cloud features. We're going back to the old model from the 70s when you had a client-server model. And the client was a little weak thing and all the processing was done on the server in the cloud. Once you have good enough network connections, that becomes the economical way to do it. Now you can have a little small portable device that can't do much except send data to the server for processing. Anyway, so the Android phone does this. What's surprising about Google is they want to be open about it. So they tell you how to log into your Google account and you can look at your Google archived history and you can listen to all the voice recordings that have been sent up to Google, which is pretty awesome. So you can see what's going up there. I know when the Barbie dolls came out about a year ago, the kids talk to and it memorizes their parents' voice and talks back to them. They found out that all that stuff was going to the cloud and everybody freaked out at privacy intrusion on the children. And I think like Bitcoin, these cloud services are not something people understand. So they are not aware that what you do with an Alexa in the room is all being stored in the cloud. They just think this gadget in front of you is doing the work and not that it's all like Big Brother. That was the whole big thing in, I think, Brave New World. They put a TV in your room and it's recording everything you do and sending it to the government. And we're all more or less there, except it's not the government, it's Amazon and Google. Anyway, so that gets us to the official time here. So I've got ad codes if anybody needs them. I handed out a few before class. And I'll have a break in about a half hour and then I'll hand out the ad codes to anybody that needs them. So we're here. The first class was motivational stuff about cryptocurrencies, which is interesting but not going to be on tests and such. Now we're down to the first chapter of the book.
Excuse me.
Next, yeah.
I'm sorry for interrupting.
That's fine.
I see the book is still $22.
Should be.
And I've got mine's like 35 or 37.
Okay, well maybe they're selling out or something. It was 22 when I looked at it at Amazon. Maybe it's gone up. What happens is, well, yeah, I guess so. It just happens is the cheap ones got sold. Affiliate link? Oh no, I don't get anything. No, I don't get anything from it. But I did. But anyway, yeah, what happens is that's it true every class, every semester. The cheap ones sell.
Okay. And on the left side, that thing is supposed to be free, But you was that, yeah.
Yeah, that should be free. There's a free online version of it for
Sure.
sure.
Give me for $7 for the electronic version. So.
Yeah, but this is it right here. That's the whole thing. It's all there.
Okay.
Yeah.
Cool.
Yeah, that's free online. That really is. And of course, if you were an evil person that would use BitTorrent and violate the DMCA, you could probably find a free copy of this one too, but none of us would ever be so immoral as to do such a thing. Yeah.
Presentation, it kind of got the link to that book.
Which one? This one?
No,
Well, I've got PowerPoints down here. Yeah. Yeah, you might. I mean, typically you want to read the book because you have to study the book before class. So anyway, they got scheduled down here. There's a live stream, which you can join. I don't know if anybody's actually doing it remotely, but somebody's doing it in class, which is fine. I like to know if it works. First couple times I did this, it was pretty messed up. I used the wrong microphone and stuff. Hopefully it's getting a little better. So if you want to participate during class, you can use the live stream. After class, it'll be a YouTube archive up here. So you can just watch the video anytime. So we're going to go through chapter 1 today, no class next week. And after that, chapter 2, and then there's a quiz you got to do online before class. You do it in the, and that quiz is already up. You can do it anytime, but it's due half an hour before class. It shouldn't be due on August 31st. It should be due on 9/11.
Email message from you.
Oh, I put up a test that doesn't count anything, just to get somebody to do it, so I could see if it was working. Because some of my other classes, they couldn't take the tests. And I think I took that down now. So that's because I was getting worried. The first week or two, people said they couldn't get any of the online part of my classes, and I think that's straightened out now. But I think somebody actually took the real test. So, yeah.
Is it on campus? It's called campus?
It's on Instructor. This is it, ccsf.instructor.com. That's where the quizzes are. Yeah, and it's somewhere in the cloud. It's somebody else's.
I got on.
Oh, I should fix that. Thank you. Oh, that's right. I'll fix that. It's really up until a half hour before class. That's left over from previous semester. Thank you for telling me. It's up till 5:30 p.m. on the day of class, half hour before lecture. Yeah. At midnight. Yeah, midnight that day. Yeah. Right?
And all the quizzes come from here?
Yes, all the quizzes come from there, and they're open book, and you get 2 chances. And all they are is a tool to encourage you to study the book. So if you read the chapter, you should be able to answer those quizzes. Yeah.
Last time they take it twice, the hardest score counts.
Right.
But
Oh, it might say that it's the first. I think what it was last semester. That's probably out of date. So it's really the higher score that counts. I tried doing it some other way, and a bunch of students complained, and I said, well, you're probably right. Why do it? Yeah. Well, I was trying to make it a measure of success, but I finally given up all hope of that and just made it encouragement to study. I've gradually become less ruthless about measuring performance. I'm really just here to encourage performance. So as you probably know, it would be pretty easy to cheat on this stuff. I don't recommend it, but my real concern is to help the honest students succeed. Even if I make it easier for the cheaters, if there are any, I don't know why somebody would cheat in a course like this, but there's always somebody. Yeah. In green. Yes, that's it. And that's what it should be on my webpage now. That's what it always is. I finally figured out how to make it quit changing. So it's 410 and all that shit. Yeah, that's all my live streams will be that. I finally found the option to lock it down to one number. The last week I was having a lot of trouble. It turns out that if you use the online page, you get a different ID than if you use the app. And it took me a while to figure it out. Anyway, so now that's the one, and it seems to work. All right. Any other questions? Well, let's just start with chapter 1 then, which is here, 141. Knowledge. All right. There we go. All right. And I actually based this on some slides that came from a textbook publisher. There usually isn't any such luxury available, but this time there is. Let me see if I can get some of this junk off the screen, or at least out of the way. All right. So, and this will hopefully help me explain something that I warned you about, which is I'm not really going to worry much about the highly mathematical parts of the book. So we're going to go, I'm mostly interested in how to use cryptography. As far as like proving theorems and stuff, I'm not looking for it, or even making new modified versions of cryptography is not really my goal here. I just want you to learn how to use the standard stuff correct. That would be enough to make you miles ahead of 90% of the developers, as far as I can tell. As far as I can tell, most companies have nobody in the company that has any clue about cryptography, and they are so bad that they don't even know how stupid they are. They think they know, and they don't know. So here's the general rules. There's a thing called cryptology, which is the science of scrambling stuff. And you're going to take it down there. Better turn down your volume. Okay. And so cryptanalysis is analyzing the routines and finding a way to break in. And cryptography is the science of applying these cryptographic routines. So somebody invents a new cryptographic routine. This happens every few years. The National Institute of Standards in America decides that it's time for a new cryptographic routine because the one that is currently the standard is not trustworthy anymore. So they announce a contest, and for about 6 years, cryptographers all over the world submit algorithms to the National Institute of Standards, who then publishes them, and everybody tries to hack in. So when they had a new hashing routine, they needed a new one to replace SHA-1 about 5-6 years ago. So people sent in dozens of candidates, and a bunch of them got hacked right away, and it got down to about 10 finalists, and then they had round after round of people attacking them. So the cryptanalysts try to use mathematical techniques to break in, and they eliminate the ones that have weaknesses, and eventually they get it down to ones that are trusted, and you end up with 5 or 6 finalists that are all very good, and then they pick one of them and gives it the U.S. government seal of approval, and then the people who sell software to the U.S. government obey that, and the industries that trust the U.S. government use that, and the people that hate the U.S. government use the runners-up because they wouldn't trust the government, for which there is unfortunately very good reason. The government has been caught several times deliberately poisoning the cryptography that has the official seal of approval, so it is in fact less valuable than the ones that are not approved. They have done that 3 or 4 times and got caught, and the more cynical people suspect that the only reason they haven't gotten caught lately is just that they've gotten better at hiding it. This is one of the fundamental problems. How do you really know that there's no other way in? Unless you're able to really do that cryptanalysis up to the world standards, somebody could have pulled a fast one on you, and there could be a secret backdoor in without the key, and you would never know. So in the old days, there's cryptography thousands of years ago. Caesar cipher was the one that Julius Caesar used, where you just move everything forward a few letters in the alphabet. And in a time when almost nobody could read at all, even a small thing like that was enough to hide military secrets to where nobody could get in. That's not enough anymore. Now you can't even use Sunday morning cartoons that way. They're more sophisticated than that. Symmetric ciphers are the only kind of encryption that existed until the 70s in public consumption. I have heard, although I think we will never know, that the NSA had this stuff 20 years secret, 20 years earlier, and kept it secret. It was until Whitfield Diffie and other mathematicians reinvented it on the civilian side that civilians got it. But the only kind there ever was symmetric ciphers, until this, which is the kind you normally think of. You have a key, and the other person you send the message to has to have the same key. This is fundamentally stupid because you have to have a trusted channel to distribute the key. And if you had a trusted channel, you don't need encryption. You could send your message through the trusted channel. So it's kind of nuts, but that's the only kind of cryptography that existed. Asymmetric cryptography is the miracle that makes the internet possible, internet security possible. It means that you can send a secret to someone without having any trusted channel at any time, because they create a key pair. So they have a private key that they never tell anybody, and they have a public key that's available to everyone, and everybody can use the public key to send a message to them with great confidence without ever having a trusted channel at all. Yeah?
This is slightly off topic, but in World War II, they invented Navajo. Where would this fall in these categories?
Navajo is actually, I would say, not encryption at all. It's security through obscurity. This is where you do something, this is where you hide the key under the mat. Like I had a friend that made a password, a simple word in Spanish. And until you think of that, nobody's getting in. So I mean, that's what I say. If you use a language nobody else knows, then that would be, it's not a mathematical scrambling, but it is a covert system. There's a similar one. If you read the Sherlock Holmes novels, there is one where you would just, this is the book code. You just previously decide that a certain personal message in the London Times meant something. Then when you see that message, it means something to the other person. There's no way to crack that. There's no mathematical pattern. The only way to crack it is to somehow get one of the people in possession of the secret to hand it over. Yeah.
How's that contrast with one-time pad?
It's essentially the same as the one-time pad. One-time pad is essentially the same thing. You have a big key, which you have to distribute. It's a secret key method, and then there is no way to crack it. The one-time pad, in fact, can never be cracked at all because the one-time pad uses a different key for each character. And so if you tried to brute force it, you would create all possible messages, and you would have no idea which one is the right message. Unlike most cryptography, you have a limited key space, and what you do is you try guessing keys until you get something that is English, or whatever language you have, and you can recognize that this stuff is English and the others are all gibberish. But the one-time pad, you will get every combination of letters, so you will get Shakespeare and every other message you want. You'll never know which message they meant. Yeah?
I'm not sure this is what you're referring to, but I just watched the Sherlock Holmes where they use the book code.
Yeah, the book code is another one. It's another secret key cipher, where you put a bunch of numbers and the numbers point to a book. That's another one. They use quite a few of these in Sherlock Holmes. I mean, yeah, and the problem with that one is you have to have exactly the same book at both ends, and therefore you can usually guess what kind of books are sitting around. But anyway, these all are symmetric systems in that there is a secret that had to somehow be conveyed to the other end. And so two people have a copy of the key, and if two people have a secret, you have no idea how many other people have the secret. He could have given extra copies or lost it. So there's a fundamental weakness there. Yeah.
So does one-time pad have perfect security?
Yeah, the one-time pad is completely unbreakable. However, it is very expensive to implement. It has the same key distribution problem. You have to distribute the key to the other person. The reason it's unbreakable is you never reuse any part of the key. However, the old-fashioned one is the only really unbreakable one, where you actually make it with something like dice, something that is really random. If you have page after page of really random numbers, and then you just shift forward in the alphabet that many spaces, nobody will ever be able to crack that without finding the pad. But if you use some kind of computer random number generator, then it might be predictable. And and it kind of amplifies the key distribution problem. If you want to send 1 megabyte of text, you have to first distribute 1 megabyte of keys. And you have to do that again before each time you send more text. So the difficulty of actually implementing it is very large. But it's fundamentally mathematically unbreakable. No one's ever found a way in. It seems very simple to understand that there's nothing will ever get in. Yeah.
Where does hash fit in that?
Hashing's different. Hashing is not cryptography. Hashing is just putting a fingerprint on a file. There's nothing random about it. It can't be reversed. If you do it again, you get the same fingerprint. It's just a way to make sure the data has not changed. That's all it does. It does not send messages or conceal messages. It just puts a signature on something so you can tell if it has changed. And that's what I was complaining about Bitcoin. Bitcoin is not encrypted. The transactions in the blockchain are plain text. Anybody can read them, but they are signed with cryptographic hashes, so it cannot be altered. Hashing gives you integrity. It does not give you confidentiality. Good, these are very good points. And then, of course, in the modern internet and other modern protocols typically mix all three things: asymmetric, symmetric, and hashing. Used correctly, combined correctly, they create things like HTTPS, which is fantastic. You can log into Google, and nobody but Google can steal your password to some high degree of confidence. There is always some issue of key handling, and there are always some weaknesses in every system, but it's really very good. The mathematics is very good. So before you had cryptography, if Alice wants to talk to Bob, she has to send her data over some insecure channel like the internet, and anybody like Oscar can get it. And this is how people steal telnet passwords and FTP and all the other passwords, because people continue to use plain text protocol over the internet, many of them, just because they can't be bothered to update their stuff, which is a sin and a shame, but that's the way it is. So symmetric cryptography is the improvement. Alice sends her data, and before sending it over the insecure channel, she encrypts it with an encryption function, E. And so what she sends is Y, which is scrambled ciphertext. And that's what actually travels over the insecure channel. Bob can decrypt it because Bob has the key. He can decrypt it back to here. Hopefully Oscar doesn't have the key, because you have somehow magically distributed the key securely to Bob without leaking it to Oscar. And therefore Oscar can't get in unless he can guess the key or find the key somewhere or find some kind of mathematical weakness in the algorithm that makes it possible for him to decrypt the message without the key. And all those things do happen sometimes. But if you use a good function like AES is the currently recommended symmetric encryption, you have a very high degree of confidence that nobody can decrypt it without the key. And then your only issue is you have to distribute the key and protect it. So this is the mathematical part of it. K is the key, and here's the set of all keys. This is called the key space. If you don't have a large enough key space, then your algorithm is useless no matter how brilliant it is. This was what went wrong with GES, which was another case of the US government deliberately poisoning the system. IBM proposed a 128-bit cipher called Lucifer, and 2 to the 128 is a huge key space. No computer can do that many calculations even today. But the government mysteriously shrunk it down to 56 bits without explanation, made that the American standard, DES, and that case is too small. And even in the 90s, around 97, they were able to build computers that could try all 2 to the 56 possible keys. And the brute force attack is the slowest possible attack. You can never stop that. Someone could just try every key and you're hosed. So the key space has to be large enough that your attackers can't get in, and that's why all security relies on threat modeling. Nothing is ever perfect, and nothing ever lasts for very long because computers keep getting faster. So before you decide if something is secure, you have to decide what attack you're worried about, and then decide if you stopped that attack. And there are always other attacks that you haven't stopped, and that bothers people, but you have to get used to it. Nothing's ever perfect. And in particular, the people with a really big problem are people with medical records, because medical records are confidential, and it's really not okay if they leak in 20 years or 50 years or 100 years. And there is nothing you can do where you can really promise that it'll still be secure in 20 or 50 or 100 years, because everything keeps changing, and that's a big problem. There is no good solution for that one. I should say, the way to address that problem is defense in depth. Not only do you encrypt your medical records, you also store them offline. You put an air gap, you put an authentication system so that even if the encryption can be broken, there are hopefully other layers of defenses that might stop the attacker. That's the only thing you can do. And the same thing happens if you have legacy equipment. Like you might have an NMR machine, and the TSA has machines that scan your luggage to see if there's a gun in there. Those things are hopelessly out of date. The things that look at your luggage are running on Windows 98. Back in the days when there was no actual login, no password, and it would cost too much money to replace it. So you have a vulnerable object, and you protect it by putting protection outside it. You don't connect it to the internet. You only let people get near it if they have a badge and they went through a locked door and all that. That's how you protect things that you can't make secure themselves. You put a layer of security around them. Yeah.
But wasn't it a big deal with those X-ray machines in the airport that they were too good? So you would like completely see a person pretty much naked. So not the X-ray machines. Those are the shortwave machines. He's saying that the question is the machines are too good and they show you naked. Yes, there is a privacy intrusion on those things where you stand up like this, where they can sort of see the outline of your body naked. They kind of lower like the position, so that's why they still have to cut people sometimes.
Yes, I've heard. Yeah.
Like a bumps, but they wouldn't see like what exactly displayed there.
Yes, this is a good point, and that's another issue. There are privacy concerns and cultural issues, so they had to lower the resolution. Yeah, and you could argue that all the TSA screening is pretty much just security theater, but maybe not. Yeah.
So how is cryptography going to respond to quantum computing? Are they just going to push up the key space, or do you have to do algorithms?
That is an excellent question. The question is, how are we going to handle quantum computing? The answer is nobody knows, because we don't really have quantum computers yet. But the NSA a year ago suddenly reversed course. They had been pushing elliptic curve cryptography for years, telling everyone to switch to it. And they suddenly reversed course about a year ago and said, abandon what we told you, and triple the length of all the keys. You better have 4,096-bit RSA. The elliptic curves that used to be 64-bit keys ought to be like 256 or something. And they said, we are trying to develop quantum-resistant algorithms, but until those exist, just take the existing algorithms and triple the key sizes until further notice. Because then, and my personal opinion is this means the NSA has a quantum computer. They're typically 20 years ahead of us. And typically when they give you a warning, it's because they have proven it's possible. But I'm just guessing. That's typically how it goes, though. Usually in 20 years, you find out that they had one. That's why they know it's coming. Until maybe 6 years ago, I think people believed quantum computers were just science fiction. They would never really happen. Now there are some prototype versions for sale from D-Wave and stuff, and people argue about them. But it's pretty clear, the writing is on the wall, that it's really going to happen. it might take another 10 or 20 years before it's reasonably available. And when it does, all the algorithms we trust today will be gone. So we got to start upgrading. And the first upgrade is just longer keys. But in a few years, they might have new algorithms. No one knows. But first, you'd have to really have it to find out what it can do.
So do you think cryptography will be able to keep that?
No one knows the answer, but I assume, the next question is, will cryptography keep up? I think it will, because the internet, if you study internet security, it is appalling, and it has always been appalling. We are just like passengers on a boat with leaks, and we're constantly patching the leaks, and then another thing breaks, and then we patch it, and we patch another. There's so much need for the internet to work that I think we will just continue to patch the problems. Same thing's true of our legal structure and our political structure. There are problems, but we don't just give up and die. We just patch them and get through another day, and then we have to put on another patch and another patch. I assume we'll keep one thing ahead somehow. But it'll certainly continue to be the case that anything that's 5 or 10 years old is no longer secure. And we'll just have to keep upgrading stuff. Yeah.
So does that mean that the science behind cryptography will still apply if quantum computers come out?
Yes. The science behind cryptography, the mathematics and science continues to be true. And that's why you can even study ancient algorithms to understand the principles, but you have to keep adapting to new attacks. Quantum computers will certainly break some of the existing protocols. We'll have to replace them with something else, but we don't really know which ones yet. So, we'll just have to invent a quantum-resistant protocol. There are ways to hide data without using mathematics. You can use quantum key distribution. That's already for sale. You can send messages with light that is so dim that it has only one photon to carry a bit of data. And then you can tell from the physical properties of the light whether someone intercepted it or not. It's like the old Mission Impossible, this message will self-destruct. You can only measure a photon once, and then it's destroyed. So if the message gets there, you know that nobody in the middle got it. So that is not mathematical. There are other ways to send secrets. So we could go to things like that if we have to. And some people are going to that. So and it's the same in all the aspects of security. The criminals keep getting better and better, so the good guys have to get better and better, and onward you go. It's not that different than the physical security. The cops get bigger guns, then the crooks get bigger guns, then the cops get bigger guns, and on you go. Yeah.
You mentioned the public keys,
yeah.
How would Alice get it to Bob?
The public key is not a secret. You put it on the internet so everybody can read it, because you can only receive with public key cryptography. I make a private key and a public key, and I put the public key on my web page, on the internet, for everybody can see it. And anybody in the whole world that wants to talk to me scrambles stuff with my public key, and I'm the only one on earth that can read it. That's how it works. It's one way. You can receive secrets. If you want two-way communication, the person at the other end has to make their key pair. But then the two of you can talk to each other with complete security, because this is a really good model. I make a secret and I never tell anybody. Now that's a good model. The part where you have a secret and you share it is fundamentally stupid. Once you've shared it, you don't really know it's a secret anymore. But in public key cryptography, you make a secret and never tell anybody. And that's a good model. The problem is there's still key distribution problems. The attack against public key cryptography is to put up a fake public key. And now I don't know which key to use. One of those keys goes to an attacker, one goes to you. So now you're back to the same old problem. I need some kind of trusted channel to tell which public key is really yours. And there's a more subtle key handling problem. I have to have my private key to read the messages, and I have to not lose it. So I can't put it in the cloud or make copies everywhere. So frequently I don't have it where I am. So now I can't read my mail. I lose availability, which turns out to be a huge problem, to where even the designers of PGP have given up using it. I've given it up to, I have about 6 public keys out there. You send me encrypted stuff with any of them, I can't open them. I lost all my private keys years ago. It's very hard with all this age of computing. 5 computers ago, one that I threw and lost on an airplane 10 years ago, had one key, and on it goes. So anyway, key handling is the dirty secret. Yeah.
Was the photon example an example of quantum key distribution?
Yes, quantum key distribution.
Is that the same thing as quantum cryptography?
Yes, this is a very important issue. That is what they call quantum cryptography. Quantum cryptography is actually a misnomer. There is no quantum mechanics involved in the cryptography. The cryptography uses some standard thing like AES The only thing that's quantum is the key distribution, where you send the key and the photons one at a time so you can tell if they got intercepted. That's a lot of people call this quantum cryptography, but the two things that really exist are quantum computers, which use the property of quantum mechanics to do calculations unthinkably fast, and quantum key distribution, where you send messages and you can know that no one else read them. Quantum cryptography is a sort of sloppy term used by journalists to sort of confuse us in the two. Those are the two things that really exist and really depend on quantum mechanics. Anyway, my free meeting, okay, well, I'll restart it. We'll just take a break when that happens. All right, so here's the equations, right? You take your X, which is clear text, you run it through E using the key, and then you get Y, which is scrambled stuff. And there's an encryption function E and a decryption function D, and they both require the key. And it's the same key in both cases. The mathematical function might not be the same, but the key is the same in both cases. So that's the game, and here's the fundamental problem. You have to somehow send the key to the recipient over a secure channel, and that's a weak spot. All right, so let's see if I can get this thing to move. There we are. So cryptanalysis is how you get a mathematical test. All of this is sloppy. It's not like trigonometry, where you prove a squared plus b squared equals c squared, and it's absolutely 100% true. It's just a matter of practicality. No scrambling routine is perfect. All it is good enough against a certain attack. And so you can't prove mathematically that it's perfect. None of them are perfect. All you do is you calculate how long a certain attack would take, and when that is long enough, you call it good enough for now. So it's no more than like a safety rule, like how strong should the stuff your seatbelts are made out of be to make a car reasonably safe. It's not like there's a perfect solution. There's just a engineering rule of thumb that's good enough in most cases, and that's all cryptography is, which is perhaps disturbing, but it does not rest on the kind of beautiful math where something is proven to be 100% true and perfect. It's just resting on opinions of people that are knowledgeable that it's good enough. So that's the game. That's why it's highly recommended that you use the standard public systems, because the public systems have been attacked by real smart mathematicians for decades, and they haven't gotten in. If you make up your own and keep it a secret, which many, many companies keep on doing, it is far more likely that you have just foolishly reproduced something that was broken decades ago by not knowing enough math than that you have really thought of something that all those mathematicians didn't think of. But many, many people try to keep their algorithm secret. So the general rule of cryptography is if you have any software or hardware or anything you buy and the manufacturer will not tell you what cryptographic system they're using, don't use it. It's almost always garbage. If they were really secure, they would use something standard and they would be happy to tell you, we're using AES, we're using RSA, something like that. Skype. You may remember a few years back, before Microsoft bought Skype, Skype was encrypted and the US government could not get in. And the head of the FBI offered $1 million reward for anybody that could hack into Skype, because their secret proprietary algorithm was stumping the NSA or the FBI, which is not a lot easier to stump in this regard. And they said eventually the secret algorithm leaked out and it was AES. But they didn't tell you what it was, but in fact was something good. Sometimes you're lucky, but usually when they won't tell you, it's because it's some garbage they made up. So you attack them. So mathematical analysis is where you do math to try to find a weakness in the system where you can get in there without trying all possible keys. If there is no mathematical weakness, the only way in is a brute force attack where you try every possible key, and then the only issue is how big the key space is. Then there's implementation and social engineering. Even if you have a system that is essentially mathematically perfect, as strong by like RSA or AES, you can still have implementation attacks, like the radio frequency emitted by the wires on the computer while it's calculating leak out the key. The time it takes to do calculations leak out the key. The amount of power it consumes leaks out the key. These things happen, and they have nothing to do with the math, but they have to do with implementations in the real world. And then there's social engineering. You just trick somebody into handing you the key or the password, which is not mathematical at all, but it's a real issue. And so nothing is ever perfect. All you can do is lock one door and there's another way in. So if your mathematical cryptography is wonderful, people will just sneak a camera into your bedroom and take a picture of the screen while you're typing it in. So they get it before it's encrypted, things like that. All right, so the brute force tries every possible key. So, 2 to the 64 is something that can be cracked these days. Like say 2 to the 56 was cracked by brute force in 1997. So 2 to the 64 is not that much of an improvement. 2 to the 128 is considered completely unbreakable at the moment. All the computers in the world running for all the time in the universe could not try 2 to the 128 keys. But people who are nervous about things like maybe quantum computers or problems in the algorithm that might be discovered in the next 10 or 20 years, so you don't really have to try all the keys, would rather use something like 256 to give you some breathing room. So even if somebody finds shortcuts, hopefully there'll still be enough work there that they can't get to the end. Yeah.
Do each of these keys require, the key links require certain requirements for hardware?
Well, what happens, you don't necessarily need any particular hardware to do any encryption. What happens, though, is if you have a really slow processor like 8 bits, it'll take a long time to calculate these slower encryption routines. The officially approved encryption schemes from the government are chosen to be fast. So that's an issue. And you can make special hardware that's faster, and that's how they cracked the 56-bit key. They made a special processor that did just DES really fast in order to try all 2 to 56. So you certainly can make a longer processor that does more bits at a time is better, and a processor that's specifically designed to do just one thing is even better yet. So those things exist. But a general purpose processor can certainly do these encryptions. They might just be a few orders of magnitude slower. There's no particular need for it to be a processor, but of course, the faster the processor, the faster you can do it. So an old classical one was the substitution cipher, and I think I'll pick up here after we take a break. Let's take a break till 5:02. I'm going to stop this stream and restart it at that time because this is going to end anyway. Let me figure out how to end.